This is the brief on the calculus of a forced oscillating string. Right, so imagine you've got a string. One end's fixed, but the other is being forced to wiggle back and forth. Now, analyzing that motion means you have to solve some pretty complex equations, and the whole key is this one mathematical strategy that actually makes the system solvable. First, the core challenge is something called an inhomogeneous boundary condition, which is just a fancy way of saying that forced end won't stay put. The strategy, then, is to mathematically transform the problem into a much simpler one where both ends are held perfectly still. Second, this transformation is a trade-off, It's not free. While it cleans up the boundaries, it pushes that complexity into the main differential equation and the initial conditions. But that's okay, because we can find the total solution by constructing it piece by piece, just adding up the three separate parts that this move creates. And finally, this is where the real payoff is. This whole process reveals that the string's total motion can be broken down into three functional components. There's the immediate shape, a temporary transient response, and the final steady wave. What's absolutely crucial is that the transient part decays to zero really fast. So the long-term behavior you actually get to see is just the sum of that initial shape and the stable forced wave. The mathematical process of transforming the boundary condition is what directly lets us break down the complex wave motion into its fundamental long-term parts.